Let's have a look at a different method for solving boundary value problems known as the relaxation method. We're going to again illustrate this using an example, and so we're going to consider the steady state one-dimensional heat equation in cylindrical coordinates. That equation looks like 1 on r d by dr of r dt dr is equal to 0. And if we expand that term in the brackets out, we just end up with d squared t dr squared plus 1 on r dt dr is equal to 0. And we're going to solve it in an annulus, so we're only going to be worried about things being a function of the radius. And we're going to assume that the inner cylinder has a radius of A and the outer cylinder has a radius of B. And we're going to say the boundary conditions are the temperature at the inner radius, T of A, is equal to T in, and the temperature at the outer radius, T of B, is equal to T out. And these are numbers that we're given. And of course the solution is only a function of radius. To solve this using the shooting method, we need two first-order equations. So for example, let y1 equal to t and y2 is equal to dt dr. We go through the process and we end up with the two ODEs, dy1 dr is equal to y2 and dy2 dr is equal to negative 1 on r times y2. Those are the two equations we need to satisfy. And we need the boundary conditions y1 of A is that and y1 of B is t out. In this case, unknown parameters are y2 of A and y2 of B. We don't know the slope or the derivative at either the inner or the outer point. So that's how we'd have to go if we're going to use the shooting method. An alternative way of looking at this is a method called the relaxation method. And so the starting point of the relaxation method is to approximate each derivative term in this ordinary differential equation here using finite difference approximations. So the solution domain is the line, is the line segment in radius that goes from r is equal to A to B. Let's split the segment into n equal pieces, each with a width of h. So we're going to say that they're uniformly spaced, and those are the points there, spacing h between them. The derivative at node I can be approximated by a finite difference approximation that we've looked at previously. So the d squared t dr squared is equal to ti plus 1 minus twice ti plus ti minus 1 on h squared, and dt dr is equal to ti plus 1 minus ti minus 1 on twice h. Of course, there are error terms that both scale like h squared for both these expressions. If we substitute these difference equations into these terms in the ODE, we end up with what's called a finite difference equation. And if we group the terms for ti plus 1, ti and ti minus 1, we end up with a finite difference equation that looks like that. 1 on h squared plus 1 on twice hri multiplied by ti plus 1 minus 2 on h squared ti plus 1 on h squared minus 1 on 2hri times ti minus 1. How does this help us? Well, first of all, at nodes 1 and 5, we're given the solution. We're given some boundary conditions. The TA is equal to T in, and TB is equal to T out. So TA is clearly T1, TB is T5. Therefore, we only need to find the solutions at nodes 2, 3, and 4. So let's write the equation explicitly at node 2. At node 2, I is equal to 2. The equation looks like that. That's just plugging in I is equal to 2 in this expression up here. At I is equal to 3, the equation looks like that. And at I is equal to 4, the equation looks like that. So at I is equal to 2, we see we have a value of T1, but we know what T1 is. Likewise, at the equation for I is equal to 4, we have an expression involving T5, but we know what T5 is. It's just equal to T out. So keep all of the unknown values on the left-hand side. That's T2, T3, and T4. Put all of the boundary condition values that we know on the right-hand side. That's T1 and T5. And let's rearrange those three equations on the previous slide. So we've moved the known value of T1 to the right-hand side, kept the unknowns on the left. That's our middle equation. And that's our third equation, again, where we've moved our known value of T5 and its coefficient across the right-hand side. So what we now have, three equations in three unknowns, which we can write as a matrix equation. Now you need to show this to yourself, but it's very easy to show that this matrix equation looks like that. These coefficients, this row here multiplied by that vector there is the first equation, that row there multiplied by the vector is the second equation, etc. And we have a right-hand side vector here, which is got the boundary values in the first and last entries. We now invert the left-hand side matrix, and we multiply it by the entire equation, and we then end up with an expression for T2, T3, and T4. So that's how we find the solution in this case. So this is the end of strict boundary value problems. We will continue to look at this in a different light, but the key things to keep in mind for this are, first of all, you need to know what a boundary value problem is. You need to understand the shooting method. So the difference between constraints and adjustable parameters, how to adjust the parameters to satisfy the constraints, and how can you turn the problem into a root finding problem. You will need to be able to do this. We've also looked at finite differences and how to approximate derivatives, and then the relaxation method, how to turn the ODE into a finite difference equation, and then how to solve this set of finite difference equations. And here is a little bit further reading on boundary value problems.